All right, let's talk about queues. Anybody have any questions before we get going? Or I should say, what questions do you have? That's the proper teacher way to do it, I guess. Anybody have any questions? What questions do you have? No? How's homework 1 going, or 2 going? Going all right? It's coming along? If you haven't, I talked to a couple people today who are like, I'm going to start it today. And I thought, better hurry. But you never know. You can get it done. Haven't been able to run it yet. That's all right, but you're getting there. There were some questions on Piazza. Some people found this function that I had commented out called read_deck, I think is what it's called. And they uncommented and said, hey, it broke. But it's because they might not have realized what it's actually doing. When you do the read deck, and you don't need to test this, you can just leave it commented out and nothing will ever be bad. What it is it's a way to read in a deck of cards without having to type each individual card. So you do read deck, and then it says, it just gives you a blank terminal, and you start typing like A, D for ace of diamonds, comma, 3, H for 3 of hearts. And then if you hit return, it'll input it as if those were the cards in the deck. That's all. If you want to test it, go right ahead. But this is one of those cases where I might say I might offer no extra technical support on that part. OK. Nobody else has any other questions about or comments on homework 2? What did you think of the lab on mazes? It was all right? Yeah, it was kind of cool. I mean, you got to see how to solve a maze and how you might do it for real life. Somebody came up in the lab I taught. Somebody said, this is how I would have solved a maze, like if I was in a maze. And in class I said, have you guys ever been in a corn maze? And you know how they always spell it corn, M-A-I-Z-E, because they're being clever, right? Well, anyway, for a maze, yeah. Well, anyway, somebody said, look, and sometimes what I do is I go in there and I put my hand on the wall, like my right hand on the wall, and then I keep following, and then eventually I get to the end. And that actually works for most mazes. In fact, it probably would have worked for all the mazes in the example in the lab. And if you want, you could create an algorithm to do that, right? Just always kind of look to your right, and if it's a wall, keep following as much as you can go forward and keep going to the right. Right? It's a very similar algorithm to the north, south, east, west, except you're just saying, look, just keep going right. You'll eventually get to the end. And that might have worked. So other ways to solve that. And hopefully you saw the differences between recursion and stack-based processing. You can do the same exact thing. Loretta.
So like for these labs, so far it's been kind of simple. So it's basically like one algorithm that you have
to
come up with. But when the labs get more kind of intricate, will we be able to, like, would you publish like solutions?
I have been publishing solutions. Oh. I haven't done it yet for the maze one, but I have been. So it's on go back to the lab page, and it says the solution on there. And somebody's probably got to remind me sometimes, because I always forget to do that. But yes, but in the future, believe it or not, the labs aren't necessarily going to get more like advanced. You're just going to learn new stuff, and it's going to be hopefully it's about the same level of an hour and 15 minutes. You can kind of figure it out. Like that's kind of the idea. But yes, I will have been and will continue to publish the solutions. All right, and don't go like copying them and giving them next year's class. All right. OK, so here's what we're going to talk about today. Unix tip of the day, Eclipse tip of the day. I got a couple short ones there. Then we're going to talk about this thing called a set. Now, I actually skipped it earlier when we were talking about list, because a set is actually very similar to a list, and I kind of didn't think I'd want to talk about it. But your next homework assignment will include a set. And actually, homework 3 is up here. I was going to post it tonight, but honestly, none of you guys are going to look at it tonight because you're probably still working on homework 2. But I should be able to get it done by tomorrow. It'll be due at least, or at how should I put this? It will be due probably a week from Sunday, maybe longer. Like it will not be any sooner than that. But that's going to be, so you know how most of you guys like enrolled in the class, and there was some issue with a wait list and this and that and whatever. Well, we're going to model that for this assignment. And it actually involves the use of both sets and queues for this. OK, so when we're talking about this, kind of think, hey, how might I model the idea of having a class and then a waiting list or two? And that's what it's about. So we'll talk about sets, and then we'll talk about this thing called queues. Where are my Commonwealth nations people? Charlie, where are you from? Yeah, you're a Commonwealth nation, right? Like the Commonwealth, right? Right? If I told you, go stand in a queue, you'd know exactly what I was talking about, right? Other people in the room might be like, go stand in a what? Right? I'm not insulting your intelligence. You probably all know this. But this is like Charlie grew up with this stuff. Like that's the name for what? A line of people who are waiting for stuff, right? And the joke is that British people do that all the time. Like they queue all the time, and like they're so used to it. Somebody was telling me something went wrong at like either an airport or something, and it was in England or something, and everybody just naturally got into lines waiting for things to like fix themselves. It's kind of funny. Sorry, got into queues. So anyway, when we talk about queues, it's basically just a line, and you go in one direction and out the other. Okay, so that's what we'll talk about. All right, Unix tip of the day. There's two things I wanted to show you, and they're both basically shortcuts to doing things. The first, which some of you guys I know already use. Let's see, if I go onto my server here and I type ls, right, it gives me a list of all the folders. What if I wanted to type a list, I wanted to see, for some reason in here I have a bunch of files called hserr_pid business, right in the middle there in white. So if I wanted to look at those, I could type ls and then hs and then hit the tab key, right? And then notice, well, you can't see because the screen's not up. Hang on. Here we go. There we go. Oh, almost. Oh, hang on. One more up. At least that'll do it. OK. So at the bottom here, see I've typed ls. And what I actually started typing was ls and then hs. And if I type tab, it says, oh, I can complete that up to a point, right? It'll start saying, hey, what in the file system will complete what you're asking for? And it says, look, there's a whole bunch of files. There's more than one file called hs_err_pid, but those are the only ones that started with hs, right? And then if I happen to know that it was the next one was, and by the way, if I keep hitting tab, watch what it does. It'll print out all the ones that would match that. So I can actually go, oh, what was it again? Oh, it was the hs_err_pid 2020. And if I type 20 and then tab, it fills in the rest of it for me. So it's a nice, easy way to fill in the details. A lot of times when we are copying files from the class website, I'll say type cp/comp/15/public. And if you do p and then tab, it fills in the rest of it for you, just like that. Because the tab completion says what else starts with p, and the only thing in that folder that starts with p is public_html, so it will fill it in for you, right? And then let's say assignments, as tab, and it fills in assignments. Homework 1/f for files, right? So I'm just keep hitting tab, and it completes it for you. So it's a nice shortcut for completing things, okay? Another related, well, actually this is related to the next thing, but other like shortcut commands, if you do the up arrow key, I think I've showed you this before, the up arrow key does the last things that you have done. So I'm right now hitting the up arrow key, and it's doing all the history of my commands. And I can just go back. And so if you keep typing Eclipse, well, if you type Eclipse, well, hang on. If I typed Eclipse and started it up, right, it would start. And then I could do the up arrow key, and then the next time I ran it, and it would do Eclipse for me. So kind of nice. It's like a little history, what you're doing. Okay? All right, another shortcut. This is actually a cool one that I've been doing. I've been doing Unix stuff for too many years. Right? I'm not going to tell you how many. But I've been doing it forever. I just learned about this like 2 years ago. It's kind of amazing. If you know that you've typed a command recently, like let's go up and I typed cat main.cpp recently. If I hit Control-R, it does a reverse search of your history. And if I start typing cat, C-A-T, it starts telling me some of the things that I've recently printed out, right? And then eventually it'll go, and then I hit, oh, and there it is. And then I just hit Enter, and it will run the command. So it's kind of cool. You keep hitting Control-R, and it'll go backwards through your commands for the previous. So I want to know all the times I've done CAT recently. I would type CAT, and then Control-R, 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 and it tells me all the different times I did that. So it's a pretty neat shortcut. It's called Control-R completion. And it's got some other neat shortcuts. So if you find yourself typing a lot, there are ways to minimize that in Unix and Linux. OK? All right. Any questions on the Unix tip of the day? OK. All right. So the Eclipse tip of the day. Back to debugging again. I know I didn't get to show you the debugging the other day. I'm not going to go through the whole debugging thing. But if you are running your program, what I've done actually is, let me move the screen down a little. What I've done is I've actually set up some things. This is for the homework assignment. So if you're clever, you can peek at what some of my answers are. But I've set a little debug point that happens to be right in this function. Well, it's in main. And then I believe I have another one. So if I go and debug this, it'll start running. And I can hit continue. And it'll keep going until my breakpoint. And then I can keep going again until another breakpoint. I happen to set another breakpoint. Now, is that the next breakpoint? Hang on. Let me see. Yeah, I think that's the next breakpoint. There we go. There's the next breakpoint. So what I'm doing is I'm in insert at index. I'm actually checking this. Well, watch what you can do up here. If you look at this little variables window, it's actually really cool. It'll tell you what the head is. And down here, it'll tell you what it's pointing at. Right now, it happens to be pointing at some let's see. Oh, a new node that I'm just creating. No, it shouldn't even be pointing there yet. Let's see. Head. Oh, head might be pointing. Oh, head is already pointing at a card, right? And the card happens to be the ace of diamonds. OK? And then if I continue running this, watch this. I'll continue running it, and it's going to come back here again because of the way I've set this up. Watch this. Now there's a couple cards in here. Head points to the card. And if I click on the card, it's now the 10 of hearts. But watch this. I can do this little arrow key, and then it'll tell me the next card. And you can just walk down the little list. This one happens to be null, so there's no card there. But if I run it again, it's going to do another one. And guess what? Head, card, next card, next card, next. Here's the next card. And you can just keep walking down this. So if you want to look at what your linked list looks like, go into the debug window, go to the variables, and start clicking those down arrows on the head. And you will go to the next, 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 next. And you'll be able to get a picture of what your linked list looks like. It's a very good way of debugging these linked lists, OK, using the debugging tools to do it. All right, I know I went through that pretty fast. But the idea is the tools are here, and you can learn how to use them and be able to debug these things a lot faster. OK, questions on that? Yeah?
So when you hit the resume button on that specific line, why doesn't it jump to another breakpoint, but it keeps running?
Ah, good question. Let's look at what's going on here. It says there's a breakpoint here. If I start walking through the list like this, right, it actually ends up getting to, where does it go? Oh, there's more to it than this. The next breakpoint is that breakpoint again. So basically, I've got it in a loop, or I've got it in, whenever I add a card, right, whenever is it add card? I forget. Hang on. Whenever I do insert at index, right, inside insert at index, inside insert at index, I've got the breakpoint there. And so if I call insert at index once, it'll go to that line. And then I hit resume again, it'll go down and call insert at index again and end up back on that line. So that's how it ended up working. Yeah. Good question. OK. I know I'm trying to beat this like debugger thing to death here, but it will become really useful to you, especially in other classes besides Comp 15 and later on in this class. Any other questions on debugging or walking through your list of pointers? OK. All right. Let's move on. I said we're going to talk about sets. A set is a very mathematical term, actually. You've probably used sets before in math class, right? A set of like the numbers, right? If I had a set of the numbers 3 and 2, right? Just there's the two numbers in there. They're 3 and they're 2. Does a set care about what order things are in? No, it doesn't actually, right? So a set is simply it's an abstract data type that says, hey, you're going to put something into the abstract data type, and you can't actually, you don't need to worry about the order. And what else? What if I tried to put another 3 into this set? Can you do that? Can you have a set of 3, 2, 3? You actually can't, right? A set is unique values. OK? So if I tried to insert another value into this set, it would be 3, 2. If I tried to insert another 3, the set would still be 3 and 2 because it would reject that insertion. OK? So that's the bottom line for sets. It's so simple that it's barely worth talking too much about, right? But it's a list with no duplicate items, and you don't worry about order. Okay? Now, under the covers, you could worry about order, or you could manipulate it somewhere, somehow, so that it is, so that it's better for searching through it and so forth. Like, you can implement an order, but the set abstract data type could care less about order, and it's not allowed to care about order. Like, you're not allowed to say to a set, give me all the values in order. You can't do that. Okay? Obviously, because it's such a simple thing, we can build it with a dynamic array or a linked list. Right? And here's the types of functions you're going to want to do with a set. Okay? A minimal set might have the following functions. Add. Adds an element if it's not already present. Right? If you try to add an element, it should just, if it's already in it, it should just ignore it. Go through the list, finds it, it's going to ignore it if it's already in the set. Okay? Remove. Removes an element if it's present. Sometimes you will have remove implemented so that it actually crashes if there's no element that you're trying to remove. Other times it'll just ignore it. If I tried to remove 1 from this set of 3 and 2, it would, in general, just ignore it, right? Depending on how you're doing it. If you've got this case where you say you have to return the actual element, well, then you couldn't necessarily do it that way. You'd have to have some dummy element, and it would be kind of ugly. But that's the bottom line there. Size. You should be able to tell how many elements are in your set. Pretty simple, right? Just keep a counter to that. Or if you're using a dynamic array, you're going to have that already, right? Is element of. That's kind of a nice one, right? If you needed to worry about the fact that when you're removing an element, if it's not there, first you call is element of, and then you call remove if it comes back true. That makes sense? Just have to call is element of, and it looks at looks through the list and says, is this part of the set? Okay, straightforward, not that hard. And I'm showing you this because you'll use it in the next assignment. Okay? You could also do some set functions like the ones you learn in math class, right? You could do union, right? If you had a set and you said to that set, give me a union of you and another set. Like if you're A and a union of another set B, it's going to do what? What's the union operator? Combines them all, right? It says if 3 and 2 and 3 and 4 were 2 sets, the union of those two would be the set of 3, 2, and 4. Right? Okay, the intersection is which one? Intersection would just be, in this case, would just be 3. Intersection, like that. And then you can also do a subtract, which basically says take out the ones that are the same in the second one from the first one. Right? So I think this set minus this set would be what? It would be this set minus this set. It's actually a tricky one. I guess you could define, depends how you define it, right? But I would say 2. You're just subtracting out what's in here, what's in this one that's also in this one, right? So the 4 kind of goes away in that case. But that's it, right? It's those are some other set functions. You can build a set to do those. And you use that a lot when you want to keep a list of items that are unique and in some set, right? Let's think about what part of, let's think about the homework assignment that we're gonna have for next time. Okay? I said it was going to be like a class list with the wait lists, right? Okay? If I took a roster of you guys right now, right? Is there a particular order for you guys? I mean, I might want an order, right? I might want alphabetical order or order by student ID or something like that. So I could impose an order. But in general, if I just want the roster, does it matter what order you're in? Like, is there the fact that you were the first one to register for this class, does that matter? Like, you're in the class, right? OK, so the class, does that mean the class is going to be, the class itself, probably shouldn't call it class because that's what we use. I'll just call it the roster. The roster for the class is going to be a set of students. OK, now, if you aren't on the roster, let's say that you weren't a major and they weren't allowing non-majors in, and you were a major but the class was already filled up, right? Then you do have a particular order we care about, right? Like not in this case, not in the case of this class as it turns out, but in many wait lists, right? The first person on the wait list is going to be the first person to get into the class, right? Okay, we need to use a different type of situation than a set in that case. Okay, we'll get to that in a few slides. But for now, we've got our roster, which is going to be a set. Okay, and by the way, let's say that Jordan here registers and then for some reason forgets to be already registered and tries to register again. Right? If he's already in here, right, then we don't want him to like take up 2 spots, right? So hopefully the set mechanism will say, no, you're already in the class, don't worry about it, right? And and try to have a better memory, whatever. Okay, all right. So as I said, making a dynamic array into a set is really easy, right? I mean, it's basically an array where you can insert anywhere and you can delete anywhere. Probably want to do it just at the end, right? Probably at the tail end, actually. And we don't care about the order. And we can figure out some of these other how you actually implement these fairly easily, right? However, there's some issues with doing a dynamic array for a set, right? If you want to add an element, what do you have to do? Like in Jordan's case, what do we have to do? See if Jordan's on the list, which means what? Walk through the whole list, like go through the whole list, do a search, right? So yeah, so you have to search for the element, and then you can append it if you're not there. All right, well, that's fine. Remove, same idea. If you want to remove Jordan from the class, because he hates the class and wants to drop it, right? You have to first find him and then delete him, right? Or find that he's not there. So you have to do this search. All right. Size, that's an easy one. And then is element, you also have to search, because that's like the definition of a search, right? What's the asymptotic complexity of these? Oh, except for which one? Size, yeah. If you kept the size, that's going to be constant. But everybody else, order n. Not so great. So doing a set in a dynamic array, yeah, it's possible. It's not the best. There are better ways to do it. Let's talk about some of the other types of things you can do. So order n except the size. What about a union or an intersection or a subtraction? How might we implement that on 2 lists? So you have 2 lists here, and you're trying to find the union of them. Yeah?
Well, the order and repetition doesn't matter for the union, so you can just add everything from B to A.
You can add everything from B to A. OK, so let's see. For union. Oh, I see. Oh, OK. I get it. OK, so for union, what you're saying is go through each one of these and then add it.
Yeah.
OK, that's fine.
It doesn't matter if 3's already in.
But that's fine. That's a very good way to do it. What's the asymptotic complexity of that?
It would be
Linear. Hold that thought. What do you think, Marana? And then
have a list, like a linked list.
yeah.
Couldn't you just take the next pointer of the tail and just point it inside of the other one?
Well, if we were trying to do the union of 3 and 2 and 3 and 4, what we don't want is, in your case, you'd have 3 and 2, and then you'd say, just tag on the other one? 3 and 4, and then what's our problem? Repetition does matter. You can't have more than the same one of the same item. So you can, if I add, if it was 2, 3, 4, and I tried to add 2 again, it would say it's already there.
It's not a math set.
Well, it is a math set. You don't duplicate elements in a math set. Oh, can you? I don't think so. I didn't think you could, but
we learned that like a week ago.
that you can?
Yeah.
All right. Well, in our union, you can. OK, so thanks for the clarification. But OK, so you get that now, though. In our set, we're only going to, so you can't do it in this case. OK, but back to, and did you have a comment? OK, back to your linear thing. OK, so I get that what you're saying is just take every element from this and add it to this.
But because I was under the same assumption that you could have repeated elements.
Oh, OK.
So if you have
Sorry,
you have to do
can't.
that. You have to also check is.
You also have to check is element before you can insert it. So what's the asymptotic complexity of union? for a or for a dynamic array? The one above linear, kind of. There's one that's in the middle that we kind of barely touched on. Well, we'll get there later, but yes. So the one above linear is which one?
Quadratic.
Quadratic, n squared, right? And why is it n squared? And this is an important one. It's n squared because you have to go through, for each element in here, you have to go through every element in there. And that's a nested loop sort of thing, right? So it's a nested loop where you have to say, OK, fine, if I'm going to do it your way, I'm going to say, for every element in here, insert into here. And that means going through this one, going through all of these, going through this one, going through all of these. And that's nested asymptotic behavior of n squared or quadratic. Not so great, right? We don't like those. We don't like asymptotic behavior if we can help it. So again, dynamic array is not the best way to implement this, to implement a union or a set, but you can do it. How about intersection? Same idea, right? You have to go through each one here and then see if it's in the other one and only add to the new list if it's in both, right? So it's the same thing. You have to go through a nested loop sort of thing. We could, well, there's a couple different things. First of all, n squared for those. It's not fun, right? We could design a set using other data structures. Later in the semester, we'll talk about some of the other data structures that we can probably, that might make this much, much faster, right? Hash table, as you can imagine, is probably one of them. There's trees, which we'll get to next week, that are also good examples of making a set a better data structure to use, better underpinning for the set ADT might be a tree, because you can do things like union much faster. In fact, you can do it in log n, which is great. We like log n. Okay? We could sort the sets. If we did say underneath the covers, hey, we might want to do union and intersection pretty fast, we could sort these sets as we're doing. Keep a sorted list under the covers. And then as we, it doesn't matter to the set abstract data type, but it might matter to how fast you do it, right? If they're in order, then you can start using some sort of binary searching ability to go through the list without going through every element. That's kind of nice. OK? Questions on the set? OK. Let's move on to queues. So queues and stacks are many times taught at the same time or right near each other because they're actually very similar data structures. Okay? The difference is that a stack was what kind of behavior? First in, last out. What was the, and a queue is the first in, first out. OK, go back to this idea of a queue being a line of people, just like I had right at the beginning of the thing here, right? A line of people to store, right? The guy that got in first, well, it's the person with the giant cart that you can't see, right? That person was in there, and then everybody else is behind them, and then the guy who's like leaning over saying, what's taking so long? That guy's at the end of the list, right? Who gets served first, at least in a queue that makes logical sense, Maggie? The first person, right? And then that's first person in. So first person in gets served first, right? The last person in gets served last. That's all the difference is between a stack and a queue. You push in on one side, you pop off the other side. But we're going to use different terms. Of course we are, right? So that's the basic idea of a queue. Okay. All right. Here's some queue operations. Okay. They're analogous to the stack operations. Right? They're very similar to the stack operations. What we want to do is we want to be able to enqueue an object, right? Which means insert at the front of the list, or sorry, insert at the end of the list. I always get that backwards when I rethink of these things. When we enqueue an object, if you walk up to a line, you get in at the end, right? Unless you're in second grade and you do frontsies, backsies with somebody or whatever, right? But I hated that, right? I hated that. It's always annoying, and it really didn't do anything for it wasn't like you got anything out of it if you were the one doing it, except for the person giving. You just gave your friend a benefit. Anyway, now I need to talk to my therapist. Okay, so all these repressed images from second grade. Gary Gerst did that to me once. Why do you care? Gary Gerst. So Gary Gerst is now, believe it or not, he is the principal of that school. right? And as it turns out, he is the nicest guy you can ever meet in the entire world, except in second grade, he just had this idea that he was also like the most popular person in high school, and so different story. But anyway, he is now I just remember, I have this like burning image of like second or third grade of Gary Gersh doing the backsies, frontsies of something, and me getting like, all upset. Anyway, all right, enough about that. So you can enqueue an object. You can enqueue an object into the back of a queue, right? To dequeue an object, where does it come off of? The front of the queue, because that's the first one that's coming off, right? So you've got this idea of having a list where you've got a front and a back. So yeah, Ben.
Why not just apply the same names to both stacks and queues?
Yeah, actually, that's a good question. Why not apply? You mean push and pop? And just have push be on the. We actually do in like C++ does that. I like to do it this way because this tells you you're definitely using a queue. Otherwise, you might not know if you're using a queue. So we just use the different terms in that case. But otherwise, yeah, they're analogous in the same way. Okay. So in an array, if we're implementing, question.
So is there no way to check for, like, so you have to go through the whole. You can only
Yeah.
access the first element. So you
Yeah.
can't check for duplicates.
No, this is not a set. Sets are old news now. Yeah, you can't check for duplicates. In general, you have the ability to get the first item and push into the last item, like in queue at the last, and that's really it, right? You can, and we'll go through some other functions we can do, but you can, in many cases, look at the front or the back. Like you can peek at the front or the back. That's easy. So we don't care. We'll let you do that. But otherwise, that's it. Yeah, Alex?
Because they're so similar, has anyone ever found would it be useful to have like a hybrid stack and queue data structure?
Very good question. There is a hybrid stack and queue type idea. Anyone know what it's called? It's called a DE. A what? I say it's two. There you go. DEQ. I wish you were around when they call this. It's called a deck, actually. And what you can do is you can. No, it really is. But what you can do is you can push or pop from either end. So it's very similar to that. So it really is a hybrid kind of idea. But yeah, I haven't seen that used too much. But I suppose there's probably cases where you might want to do that. I mean, in the supermarket thing, it's like you want to get somebody go off the end is the one who, when they open up a new register, kind of sneaks over and jumps in, right? It's kind of like backsies, frontsies. But anyway, call my therapist. Okay. So here's kind of the basic idea, right? If you have this array, and we will go through this example, we'll go through an example in kind of excruciating detail in a few minutes. But if you have an array, right, if you put in an item, let's say we enqueue 3, right, we would put it like right there, and then we would enqueue 4, might do it right here, right? Where is the front of the queue? It's this is the front, right? And you might think that this would be the back. It's actually what we're going to define this. Bear with me. We're actually going to define this as the back. It has to do with making the math a little easier. But the idea is the one that's the last item is the back minus 1 position. That's all the difference is, right? But the point is, if you want to enqueue again, where's it going to go? The next person who comes up in line goes where? The end, right? So we're going to put 5 here. And then back is now going to point up here. Right? And if we dequeue, which one comes off? The 3 comes off. Actually, I'm going to even leave it there. And the front is going to now point here. So that's the idea. So you've got an array of values, 3, 4, 5. And the front is to the left. And the front is to the left and the back is to the right, which is kind of makes sense, but it seems like you're doing it in kind of reverse order, which you kind of are. Yeah?
That's how it works. Is it important to also delete 3 afterwards?
Is it important to delete 3? What do you guys think? What do you think?
I think that we basically did delete 3 by not carrying it. Well, it depends on if we're allocating memory dynamically or not.
Well, hold that thought. It depends if we're allocating memory dynamically or not. Hold that thought. For an array, it's a little more subtle than that. For a linked list, yes. If this was a linked list and you were doing this, then yes, you'd want to delete the node that just came off the front, right? If you were doing that. But for a dynamic array, we have to be a little more clever, which is why this is a bigger topic than, oh, this is what a queue is, right? So you'll see. Other comments? Cam, did you have a comment? No, OK. What else was I going to say about this one? Oh, yeah, so back to arrays in general. If I ask for an array from the memory system, what value is going to be here? It's not 0, actually. What's going to be here? Random dead squirrels, as they say in Comp 11, right? Random stuff is going to be in here because C++ allows you to just, it says, I'm not going to bother, like you want this fast, I'm not going to make them all zeros. Boom, here's what you've got, right? There's some other things under the covers that sometimes if you give it back, it generally zeroes it out. But it can do that at its leisure, right? But as far as this, you don't know what's there. So to go back to the comment that said, hey, look, by moving front over here, we have basically turned this 3 into a question mark because we're not allowed to know what it is anymore. But did we need to delete it or do anything with it or zero it out? No, we don't really care, right? We might care if this was a security issue and this is somebody's password or something. Like, right, we might care, oh, look, if the password's bits are coming out the end of the front of the queue, then let's make sure we delete them so that nobody can look at our memory and sneakily find our password or something. But that's a security issue, not an issue of, in the general sense, doing that. So to answer your question, no. You don't need to actually delete it. The fact is, you know where your queue elements are by knowing where the front and the back are. Well, by knowing where those two things are. All right? OK, so that's kind of, yeah, sure.
If we deleted 3, would it only delete 3, or would it delete the entire array?
If we well, yeah, if you actually tried to say delete 3, it would probably segfault. Because you've probably asked for this much space. And when you try to delete 3, because I don't know what you're talking about. If you did delete with the bracket notation, it would delete the whole thing. Yeah, so you don't want to do that. Nathan, I'll get to you in 1 sec. Yes?
So do we have to move the items to override the 3 if this is an array or just?
No, you'll see in a few minutes what's going to happen. But yeah, good question. You'll see what happens in a few minutes, though. Yeah, very good question. Nathan?
When you have to expand the dynamic array you're using, you could just, instead of copying it all over, you just start at the fronts.
Yeah, that would be a very good point. You would, if you were going to do that, if you were going to expand this array, you would start copying just at the front, not at the beginning, right? So yeah, very good point. I've got a more clever solution than that, and you'll see it in about 2 minutes. Charlie, do you have a comment?
I was going to ask what you're
You're going to say the same thing about that. OK, yeah. So, sorry, what was your question one more time?
Do you have to move?
Oh, yeah, you don't. Do you have to move any of the elements over?
Yeah, to override the one that you just.
No, you do not. Nope, you don't. Because first of all, they're already in order. You don't have to move them this way. We move the pointer to front and pointer to back instead of moving I should say the index value of front and back. It could be a pointer, but in general, we're going to have an index value of the front and the back, right? So in this case, we've got, if I wrote the indexes up here like this, I wrote the indexes 0, 1, 2, and 3. Right now, and the actual array is 3, 4, 5, and then nothing, right? Or we have no idea. The front is now at index 1. And the back is now saying at index 3, which is the next possible place to put in something. OK. All right. Everybody's got the basic idea, though, of what's queues. In the back, out the front, that's the deal? OK. Some of the other things we could do with queues, we could obviously get the size. Like, not if you're doing a dynamic array. If you're doing a dynamic array, the size is tricky, as it turns out, right? You'd think it might be like back minus front. 3 minus 1 is 2, which is how many elements are actually in here. It gets a little trickier. In this queue, that's exactly what it is, but it gets trickier. Like, for instance, well, not quite a for instance, but at the beginning of a queue, when we say, when we don't have any elements in it, front and back actually both point to the same location, which is odd. Because back, that means this is the next place it can go. If front is pointing here, it kind of says, hey, this is the first one that we can take out. But if there's nothing there, then you got to watch out. So it's like a corner case, right? You want to check and make sure that, like in this case, is empty, which I guess was on the last one. Is empty is true, or not true, in order to dequeue. Okay. All right, we could print the queue. That's kind of an extended function. You would have to, under the covers, be able to go through the whole thing. Or you would have to DQ, 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 but it's up to you. You probably, if I said print the queue, I would not want you to do all that dequeuing. I would want you to actually, under the covers, walk through it. Is that your question, Susan? Oh, okay. Did you have a question? Comment?
But I answered it.
Okay. All right, so we get size, print, element, front. Here's the one where, for somebody who, I forget who asked and said, look, can we look at the back and the front in this case? Sure. If you implement a front method, that peeks at the front and says, hey, this one's at the front. And if you implement a back method, that says, hey, this one's at the back. So you could do those methods as well. OK? All right. So I already wrote this one on the board. So this is the part where you actually see the array. And we're going to walk through an example of this. Now, it will go as slow as necessary because, well, almost, we're not quite to the example yet. We're going to do a little brief example. But up here we have 4 elements in the array. I haven't put the question marks up here. On the HTML version, if you happen to look at that one, I did put question marks in there saying what they are. It makes the tables look better. But in this case, there are 4 elements in here, right? The current size for the queue is 4. All right? And have we already done some dequeuing on this one? Yeah, you can tell because of where we are in this for this example, right? We've already done some dequeuing for the first 3 there. And you can see that the front is pointing to 5, so that's the next one that would get dequeued. And then if you were inserting one, it would go after the 1. So 5, 2, 7, 1, and then after that is where the next element would be. Good? All right. So let's just try a couple things here. Let's enqueue. To enqueue an element, here's what you do. You set the element to where back points to, and then you increment both the current size and back. Very straightforward, right? What that would look like is this. It would, if you enqueued 8, right, it would set 8 to where back is, and then the current size and back would get incremented, and it would look like this. Yes, Susanna?
Is that in front of pointers?
OK, good, very good question. In this case, let's consider back and front indexes, not pointers. They could be pointers. The problem with pointers is it makes it hard a little later, as you'll see. If it was a linked list, if it was a linked list, they probably would be pointers, but they'd be like the head and the tail of the list, right? Yeah. In this case, in this array, we're just going to say front and back are actually integers that say what the index is. In this case, front is 0, 1, 2, 3. That's the index for front. 4, 5, 6, 7, 8 is the index for back. Okay? And in this case, you can do 8 minus 3 gives you 5, which tells you what the current size is. So somebody might argue, oh, you don't need to keep a current size. Just do that calculation. Fair enough. It gets a little trickier. Okay? All right. We get this, though? So far, so good. Some of you guys have already cued into the fact that we've got an issue up here at the front of the queue. Like, once you dequeue things, well, first of all, we asked we had to delete it. We're not going to delete here, right? Nathan says, hey, we're going to just start copying from there if we're making it bigger. Well, what is the, oh, sorry, I didn't go through dequeue. Well, yeah, let me just step back for 1 sec. I'm 1 slide ahead of myself. To dequeue an element, what do? Take the front one off, and then do what to front? Increment it 1, right? So that's all. So it would look like if we were dequeuing here, it would just move front over, and it would return 5. Do we need to do anything with the 5? No, we just leave it there. We don't care. It's dead squirrel. We leave it there. That's that. But now, it's the same thing. Now, even though it says 5, 2, 7, 1, 8, there's actually only 4 things in the queue, starting with 2, 7, 1, and 8. Make sense? All right, so it gets a little bit tricky here, but it's not too bad, I hope. Question?
So like if you like move the front like 1 index, like we just did right now,
Yeah.
can we just access 5 by just saying the array from -1?
You could. Yeah, sure, you could. But that's not allowed in a queue abstract data type. So you could, but you're not allowed to do that, like according to the data type. Under the covers, I mean, look, if you want to make it so, hey, what was the last one I returned? You know, you might get away with that in some cases, but there'd be lots of corner cases there. We'll see why in a minute. Yes?
So if you had like 2 queues in a row and you wanted to like take that 5 and take it from the front of the first one to put it to the back of the next one for some reason,
Yep.
could you kind of just move the front and then move the back of the next one?
Yes, but you'd insert the 5 into the other one at the right place and then increment the back. But yeah, sure, you could totally do that. Charlie.
When you're allocating new memory for a dynamic array,
Uh-huh.
can you request the specific address to start allocating that?
No, you can't. Well, it depends, but no, in general you can't. I just looked at something the other day that indicates that you could do that, and I have never programmed that. But yeah, you can't say I want it at this address. So yeah, I like the way you're thinking though. You're like, maybe we can do something about this craziness about, hey, I DQ'd all that and all that empty space is sitting there being ugly, right? Yeah. So let's see. We don't need to remove anything because we've got the dead squirrel. All right, this is where I was getting at before. What's the problem with this? Like, what's the real problem with this whole implementation here in a dynamic array? Think about it for 1 second. I've already mentioned a whole bunch of things, and people have been thinking about it and like mentioning various things. A couple people had their hands up. I'll let both you guys answer. What do you think?
I think that the problem is that like we could be like putting stuff on and taking stuff off and putting stuff on and taking stuff off, and then
Yep.
we could keep the list or we could keep the queue very small, but just by doing the operations, we would be moving it across memory and eventually reach the end of our array.
It's exactly right. You would eventually reach the end of the array pretty quickly. How many elements in this array do you have to do before you're done? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you've got to expand. But you might have been dequeuing along the way, and you've got all that empty wasted space. Wasted space. What were you going to say?
I was going to say we're kind of using the middle, and there's like we can use the back portion, the
Yep.
right portion, but there's stuff on the front.
We've totally wasted the stuff on the front.
Yeah, you can't
Yeah.
use it unless I guess you can't use it all.
You can't use it at all, right? Right? So this means that, like, if we're going to do this, we're going to have to be like expanding this a lot, right? And now Nathan's absolutely right. Don't expand more than you have to. If you know that you've used up the first 8 elements and they've already been dequeued, don't create an array that's twice the size of your capacity anymore, or do it and just know that you're going to, you've already wasted some space there. But that's a good question. That's a good point. Yeah, Morena.
What if, and this like would be better for a linked list than for an array, but if you made it a circular list, and then you could just keep going and going.
We did talk about circular lists, didn't we? Yeah. Now with a linked list, a circular list I'm not sure would help you much in a linked list, because every time you're going to create a new element to enqueue, you have to create a new node, and you do have to put it somewhere. And so you'd have to break the list somewhere and put it in. But I do like the way you're thinking. Comment in the back and then out. Yeah.
I'm just wondering, are we allowed to change the pointer for the front of the array, or is that just asking for a memory?
Yeah, you can't do that really. I mean, you can't say, I'm giving you back this part of the array. You're not allowed to do that. Nope, it's just not allowed by the memory system. Yeah, it's definitely asking for a memory leak, or for that matter, a segfault. But yeah, good question. Alex?
Oh, I was just wondering, if we were to make a linked list, would there be an advantage to implementing a circular linked list? Because like we are deleting the nodes that were popping off anyway.
Right. In this case, for a linked list, this is it's slightly different idea. You are deleting the nodes. So I'm not sure a circular linked list would make sense in this case, but I like the way you're thinking, Moretta. So very good point. Yeah.
What if when we reached the end,
Yeah.
we started adding stuff at the beginning and
What if we started adding stuff at the beginning? Do you think we could keep track of it? I bet we could.
have to subtract the size, you just have to subtract the capacity from back once you got there,
Yeah.
and then you could move around the thing.
Yeah, you could move around. That's exactly right. Okay, did you have a comment?
Well, I was going to say it's like it's all filled up and you're looping around the front or whatever,
Mhm.
and it has to get bigger than how, like if you expand, like how are you going to move things?
Yeah, if you expand now, in next week's lab, you will do that. You'll expand a queue and you'll see that it's a little tricky. You have to figure out exactly what to move and where to move it to. But it's not impossible, but it is a little tricky. Now, let's go back to your comment. Here's the one thing I want to put up. So first of all, there's wasted space. We get that, right? This idea of we've dequeued from the front and all that is wasted, okay? But here's as I like to say, the dirty little secret about most queues. Now, this is not like Comcast, because their queues get huge and it's not this idea. But in general, let's say you're a supermarket, right? At the beginning of the day, hopefully, well, at the beginning of the day, you have 0 people in their queue. At the end of the day, you have 0 people in your queue. right? And in the middle of the day, the queue can expand and contract in terms of like how many people are standing there in line. And if you go to Market Basket in Somerville at 5 p.m., forget it. The lines are out the door. But you can, in general, think of a queue as being some elements are getting in-queued, some are getting de-queued, some are getting in-queued at roughly the same rate. Now, there are times where there's going to be more getting in-queued and then less getting de-queued. So it will expand a little bit. But the whole point is, in general, if you're dequeuing, like not if you're in a queue that just stopped, right? You go to the supermarket, you stand in line, and then the cashier quits, and they never update the line, right? And the line just keeps getting bigger and bigger and bigger. That's not really what the general model for queues are, except Comcast, but different story, right? So you end up, what you end up with is a situation where you're only using part of that array. And so I like the idea of don't have this wasted space, let's utilize it. Okay, let's utilize it. Now, you guys all thought queues, these are easy, and they are not hard, but then this next step, you're like, oh boy, here's where it gets to be interesting. Okay? We implement what we call a circular queue. Okay, and all we're saying is the only time you ever have to expand this is if you have indeed taken up every space in the capacity of the array. Okay, watch what happens here. And this is where we got to spend a little time going step by step by step, just to make sure we get what happens here. What we do, right, is we actually, when we get to the back of the array, I shouldn't use that term, when we get to the end of the array, instead of going off the end, what we're going to do is we're going to set back, if we're dequeuing, we're going to set back all the way to the beginning of the array. Just set it to 0. Okay? There's actually a very easy way to do that too. We'll talk about that in one sec. Okay? And then you can start using more of these like dead squirrels, if you will. Okay? All right, I thought there might have been one other. Yeah, well, here it is right there. This is the one where when you get to this point, that's after the array, set back to 0. And you've now got to the beginning. Now you're at the beginning of the array, and we can do that. Okay? Watch how it works. We're going to go through it at least once, maybe twice if it's still a little confusing. But watch how it works. Okay? Here's what I've done on these next few slides. I've put 2 steps, and then what I do is I just kind of bump the bottom step up to the top so you can see what's going on. So this is, you'll see, I've labeled the steps appropriately, I think. Let's say we start out with a queue that looks like this, right? It's got 10 elements in it, or it's got 10 spaces. That's the capacity, okay? And the front is at 8, which is at position 7, 8. Yeah, position 7 up there. That's the 8. Okay, the back is at the last element. Okay, and remember, the back points to the next available space. So we've got one more space before we have to care about anything. So we in Q1, well, before we have to change the way we put in the things in here. When we in Q1, what happens? We put the 1 where back is, and then we increment back. Back is too big now. It's over the size of the array. Okay? Now we just set it equal to 0. Stop for a second. Let's figure out the math how we might do that. We talked about it during recursion, actually, a little bit. How might you go from, I'll let you answer. Let's let everybody think about it for a minute. How might you go from the position after the array? By the way, what index is the last one? If there's 10 things in this array, what's the index of the last one? 10, right? OK, so when that's 10, there's a couple different ways you could do this, right? Let's say this is now the capacity of the array, 10. OK, now we want to turn that 10 into 0. So there's 2 methods that you could use for this. There's the kind of the straightforward, easy to conceive of one, and then there's another sneaky one. Think about it for 1 sec, then I'm going to let you go. Think about it. Questions or answers? Answers, OK, hold on. What did you think?
I was thinking you could just increment it pretty simply and then just do mod 10.
Ah, is that what you guys were going to say? The mod 10? Yeah. So if you increment it, if you say, in this case, back plus plus, right, modulus the capacity, right? What that does is it actually creates a circular sort of thing because, so you get, what did we say, a lower number modulus a bigger number was. So 4 modulus 10 gives us what? Remember that? Yeah, it's 4 actually, right? Because it's 10 goes into 4 0 times, and there's 4 remainder. All right, 5 modulus 10 gives us 5, etc. 9 modulus 10 gives us 9. 10 modulus 10 gives us what? Back to 0 again, right? Woohoo! OK, so we can do it that way. And then what we can do is we can now say, you probably wouldn't want to do this exactly like this, right? You'd want to say something like this. Back equals back, whoops, B-A-C-K, back plus 1, the quantity, modulus capacity. That would then do it, right? You could do back plus modulus, and it would still work. You just kind of keep increasing your back forever, and it doesn't actually matter. I mean, you'd probably eventually run out of digits, but it's not a big deal. But you could do this way. There's another easier way, or not easier, another kind of conceptually relatively straightforward way, maybe with an if statement. What would that be? Yeah.
If it's greater than the capacity, then you just go and set back.
Yeah. So back plus plus, right? And then if back is greater than the capacity, actually not greater, equal to capacity back equals 0. I don't care which one you can do. You can do either one of those. But either way, that will get back to the capacity of 0, or back to the 0 place. Yes?
So it wouldn't crash on us as soon as it went beyond capacity?
Well, as long as we don't access the point after the capacity, it won't. So remember, back is the index value of what we're going to look at. So in this case, we're going to say, OK, when we in Q1, we're going to increment back. Now back is going to be equal to 10. And then we check and we say, if back equals 10, make it 0. Or back equals back plus 1% modulus capacity, and that will also turn it into 0. Good? Yeah, Janae.
What if we box through to the back and then say we don't DQ and
Yeah.
keep enqueuing until we are on the same?
Yeah, good question. If we keep going until we end up where we just keep enqueuing, enqueue until the back equals the front, then you have to expand.
So you have to expand, but the space in between, how will you move?
Yeah, that's something you have to figure out in the lab. Now, we can talk about it. If we have a couple minutes, I will go back to that question. But the idea is, how do you expand? It's a little tricky. It's not hard, but it's a little tricky. OK, yeah, very good question. Let's get through the rest of this example here. OK? All right, so we see what we've got here. We've got the current size. This is where it's really important to keep current size. There are ways of sneakily using math to figure out current size, but it's tricky, and I would avoid it if you can. If you want to go and figure it out and test it and make sure it's OK, I'll show you how to do it at the end, but it's not. I would just keep the current size, because it's easy. Every time you enqueue, add 1. Every time you dequeue, decrease by 1. Right? But we do that. Now, so we've enqueued 1. All right, let's do another enqueue. 3, same business, right? We've now gone and we've put the 3 where back points to. We've incremented back. We're done. Good? All right. Let's do 2 DQs. So from the top there where you've got the 8 is the front, we're going to DQ 8, and we're going to move the front to where 4 is. That's the first DQ. And then we're going to DQ 4, return 4, and then we're going to put front where 1 is. Did we delete 8 and 4 or do anything with them? No, don't worry about it. They're dead squirrels. OK? Notice we now have a current size of 2, because the only elements left in the queue are 1 and 3, the end and the front. OK? Is everybody with me? OK. All right, so we've done a couple DQs. If we DQ again, we take the 1 and we return it and we increment front, and now we do this business of wrapping front around again. Right? So front is now front equal, or if front equals capacity, front equals 0, or front equals front plus 1% capacity. That's how you wrap it around again. Okay? Let's do one more DQ. Right? We DQ the back, or we DQ from the front, and the 3 gets returned, and then back now equals front. Right? And now how many items are in the queue? 0, right? And if you, the only other time back would equal the front is exactly what you were saying, if we end up filling the whole queue, and at that point you need to expand. Okay? I think we do have time to go through the expansion. Yeah?
Wait, so say we want to add something to the queue now.
Yeah.
If the program sees that back and front are now pointing at the same cell, would you just assume that the array is full, try to expand it, even though there's space?
Right. So what do you have to check? Current size. Yeah, you must keep track of that. Yeah, this is a situation where that's the case. So yeah, if you don't keep track of that, you have to be really careful. Like there are ways to figure out if well, actually in this case, I don't think there's a way to figure that out unless you're keeping track of it in some form or another. Good question. Okay. All right. Let me do this because I said I would go back and do this. Let's see. Let's go to the situation where, I don't know if I have the situation where, let's pretend we're at this situation here. I'll write this one on the board, okay? Because this, I think it's worth taking the time to actually figure this out, okay? All right, so let's say we have a queue that's 10 elements. Sorry, my size is not the same. 10 elements. Let's put some elements in here. 3, 9, 4, 5, 2, 7, 1, 4, 3. I did go too many. There we go. All right. All right. And let's say that the front and the back both point to the 5 in the middle there. OK. If I wanted to enqueue now we know that the current size equals 10, and we would have to expand. OK. What do we do to expand a dynamic array? Create a new array. How big? Twice the size, right? Same idea. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, da 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 da. OK? And then we want this to be a queue again. If we just copied the numbers, right? 3, 9, 4, 5, 2, 7, 1, 4, 3, we're kind of going to be in trouble, aren't we? Because if this is the next available position, which means that this is the front, right? Well, really, we want the back to be in between the 5 and the 2, right? Like we kind of want the back to be like in between there, and that's the issue. OK, so where should we start copying? What's a good method for where we want to start copying in this case? If we're going to copy everything over to our new queue, so we reset the situation, how might we want to do it? Becky, what do you think? OK, that's right. Good.
Don't you want the back to be in between the 5 and 4? Yeah.
You want the back to be in between the 5. Let's see. So this is the front. You're right. Thank you. You want the back to be between the 5 and the 4. There would be where the back is kind of next time. Good point. I think. That makes sense? Yeah. OK, so then do you have an idea of where we might want to start copying into our new array?
So we just start from the front and then...
Yeah, start from the front, walk up, but remember to wrap around, right? So you're going to have a for loop that's up to the capacity, or up to the capacity of the current size, right? For loop, but you have to be careful about which ones you move, right? Let's write it. For int I equals 0, I is less than current size, I plus plus, right? OK, and then what are we going to? So we're going to copy. Let's say this is called the. Let's call this is the n queue for new queue, and this is just q for old queue. OK, we're copying into the new queue that we just created from the old queue. OK, so what am I going to copy? I'm going to say new queue what? New queue I, which is going to walk through from here to here to here to here to here to here. Good. Equals what? Equals the old queue, and this is the part that's the tricky part, right? What is it? OK, it's going to be front to start out with, but what? Plus I. OK, I like that, because that'll go here, 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 here. And then what has to happen here is what? Modulo capacity, right? Or size, I guess, but it doesn't matter. So how about something like this? Front plus I modulo capacity. Oops. Let's see. Yeah. Would that do it? I think it would do it, right? So what this would do is if this is the front, OK, it would go 5, 2, 7, 1, 4, 3, 0, 1, 2, 3, 4, 5. OK. And then this is actually, yeah, and this is copying from front. So it would actually copy from position 0, 1, 2, 3, 4, 5, 6, 7, 8. Did I mess up here? Is this not 10? Oh, it's not 10. You're right. It's 8. Sorry. So, oh, yeah, I guess I thought I had 10 up there. Well, anyway, whatever. I screwed up. So, yeah, so it would get up to the last one there. When it gets to 9, it would then wrap around because of this capacity and then start copying from here, the other 3. 3, 9, 4. Where would I set my front? After the for loop, front now equals 0, because it's the thing here. Front equals 0, right? And where's back equal? Back actually equals capacity, which is the old capacity still, right? It's the next available spot. So it's got to be capacity, yeah. So we're going to set it equal to capacity. And then now this is going to point here. And look at all this extra space we have, right? So kind of nice. OK, that's how you do the expansion. Does that make sense? Yeah. Go back and like walk through this again. I'm sorry I didn't put it on the slides, but I didn't think we'd necessarily have time to do that. But that's the idea. Yeah, Jordan.
With the for loop, can you still use the integer I, or does it come?
Depends where we put I. If I declare it inside there, you can't. Yeah. If you wanted to declare it outside, you might. Yeah. I mean, back equals I. You know, you could probably figure out what to use that if you wanted to. Doesn't matter to me. OK. So I've pretty much done next week's lab for you. All right, but that's all right. You'll get another chance to practice it, right? But it's the idea. There's other ways to think about it too, by the way. I mean, I've had people actually DQ, 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 DQ 10 times, and then InQ in the new one, and that works. You just have to be a little careful about what your front and back are for the new queue. That would work. But there's other ways to do it too. But this is the looping method. OK. All right. So let's go back to where we were. We said that we were there. OK. Again, you've got to rely on current size unless you want to do some fancy math. And then even if you do the fancy math, you've got to be really careful when they eventually become the same. You could have something where right when they become the same, that's when you do the expansion. Fine. You could make it work, but you have to be really careful about it. Here's the little the way you could figure out current size if you wanted to. Back minus front plus capacity percent capacity. That would tell you how many elements are actually in there. For this one, it's actually very weird. Back minus front. 1 minus 7 plus 1 minus 7 plus the capacity, in this case, is 10. That quantity, modulo 10, happens to be equal to 6 plus 10 is, negative 6 plus 10 is 4 modulo 10 gives us what? 4. So it actually works for this one. Yeah. Did I do that wrong?
No, I still don't do math.
Yeah, that one actually works for that one. Right? So you could do it this way. It's just a little bit trickier. Yeah?
Why do we need plus capacity? Won't modulus just make it work?
So what's negative 6 modulus 10? The computer will do it. It is 4, as it turns out. Right? It is 4. And the computer would do it. I think you have to be a little careful, though. It's a modulus for negative numbers gets a little like it's defined. In some cases, it's undefined, depending on who's doing the calculation. So you got to be a little careful with that. Yeah. All right. So you could do it that way. And anyway, you could, but I would just increment when you NQ, decrement when you DQ, and you're done with it. Right? Easier to do it that way, and less error prone. We already talked about this. What happens when you actually do the expansion? Be careful. Right? Think about what you're doing expansion-wise and how we use this modulo to do that. By the way, you wouldn't necessarily have to use the modulo. You could have other variables in there where you say, look, I'm going to go from front is the first one I go to, and when it gets bigger than the capacity, then wrap to 0. I mean, you could do that, but using the module is kind of fun and nice to know that it works that way. Okay. All right. What kinds of examples of real-life queues do we have? Right? There are zillions of them. Queues are like a big, it's kind of like stacks. There's like a lot of different uses for them, probably even more so for queues. Like anytime you need to do something in, first out order, use a queue, right? Printing queues. You guys all go and you try to print at the same time. Well, they get lined up, and the first one that comes out is the first one they printed. It would be bad to use a stack for that, right? Because the first guy would never get his job done, right? If anybody else came along. Ticket counter, supermarkets, a file server, same thing. If you ask for a file and somebody else does, you get it first. That's the way it works. Call centers, Comcast, right? Your call will be handled by the next available agent. Well, that means that you're in some queue waiting for that, right?
Very important to them.
And very important to them, yeah, exactly. We're very important to them, exactly. How about roster or wait lists, right? For a wait, we've kind of ignored this on the board up here, but we've got our roster, which is our set, and our queue is now going to say, right, who's in queue, and we can actually order them, and the first person in the queue should be the first person out of the queue, right? Like if you sign up, if you get a really good registration time and you sign up, you should be able to get a better chance at getting in the class. Like that's the way it's supposed to work. In this case, in our class, it didn't work that way. That's what your homework assignments for next week is going to be about. Okay? Another point of using queues is my own research, right? It turns out when I did my PhD, I did research, and I happen to use a queue structure for the type of research I did. This is actually a slide from my thesis defense, and literally it said the scheduling algorithm applications are moved from the main queue onto a device sub-queue based on a set of rules, and then I have this crazy flow chart here that tells you all the rules. But basically it was, here's my research in my elevator speech for research. I have all these things that I want to get done on two different processors, a graphical processor and a main CPU. And I want to figure out which one I should send the next job to. Well, the jobs line up in a queue, and then I decide to dole them out to whichever processor's got the most ability to do that job in the next case. So that was my research, right? Sounds a little like it's not much for 5 years, but it was. 4 years, right? What? But that's the point. So yeah, so there's lots of times you use queues, and I mean, you know, real life research uses queues as well. Okay, let's see. I think that's about it. Questions on queues, on sets, homework 2, lab. All right, I'll see you guys Monday.